So I was saying, we're standing between lunch break and coffee, so we'll try to keep this lively. We've had a lot of great talks today about threat intelligence and how high-level talks about the org, setups, and so on. We're not going to talk about producing threat intelligence as much as we're going to talk about consuming it in our forensics investigation tools. So for the next 30 minutes, we're going to be talking about our love-hate relationship with data. It's a very toxic relationship, but we're going to talk about it anyways. We're going to talk about Timesketch as well. Who here has heard of Timesketch before? Okay, who here is using Timesketch actively every day? Nice. This is what we want to fix. We're going to see how Timesketch integrates with CTI sources using Yara, third-party threat intel platforms, and Sigma. We're going to also talk about how we can share analyst approaches, and we're going to briefly have an outlook and recap of what we said. So there will be a slide at the end that you can take a picture of, and it contains all the good stuff of the presentation. So anyways, our problem, which is our toxic relationship with data, is that we have too much of it. We've been focusing a lot on collecting forensics evidence from various different environments, various different sources. The consequence is that now we have too much data. So for example, on a fresh install of Windows Server 2022, we have a total of 4 million events that an analyst has to go through in our timelines. So we have about 50,000 PE events, so compile timestamps, directory timestamps. We have 350K user journal events, 400K registry events, 3 million file system events, which are usually the most interesting ones, and that's a lot. And that's on a non-used system. On a used system, we can go to 60K browsing events that we have to look into, or 40K process execution events, and that's for like 1 day. So if you're looking at the past week or month of activity, it can get pretty hefty. And we're not even talking about other sources like NetFlow, DNS, or even other system logs. So our problem is this, and our hypothesis is that maybe we can make this problem go away, or at least increase the signal-to-noise ratio by integrating threat intelligence into our timelines. So we're trying to prune the timeline. I'm Tom. My goal is to automate myself out of a job to be replaced with a small Python script that does everything. I love automation, and I love connecting systems, and I'm also a little bit of a threat intel nerd. Alex says I'm a better coder than him. I'm not sure about that. I do know that I bought a rowing machine from him, and I never use it.
I like to talk about data investigations. I hate too much data, but I also love a lot of data. I have a failed career as a software engineer, so I tried it, I failed, and now he has to review all my code. And he bought my rowing machine, so I got a PS5. That's nice.
It's a way better deal.
Yeah. So what is Timesketch? Timesketch is awesome. It's a tool to collaboratively work on timeline analysis. It's written in Python. It's MIT. It's open source. You can use it, and it's powered by OpenSearch. So there is a foundation that can scale a lot. You can upload timelines, and you can run analyzers over it. And it has a tight integration into like Log2Timeline, Plazo, DFTimeWolf, Turbinia, and we have some cool new features. Remark here, Timesketch does not parse data. The parsing is done in Plazo. So that's Timesketch. Now, for those who have not used Timesketch before, this is how it looks like in the new UI. So this is like 4 weeks old. You can upload a timeline. You see a nice chart on how far you are. And once you're done, this file is produced by Circle, so thanks for that. It will tell you how many events you have in your timeline, and then you can start exploring it. Just like that. So you see the wheel spinning, it's ingesting, and depending on the power of your machine, it might take a few seconds, 2 minutes, 2 hours.
This was going to take 2 hours, so.
Yes, and then you can see like how fast it is, and then you can look at the data, and you can see how many events there are and so on. Now, if you want to explore data, you can start with like simply searching for an IP address, and it will show you all the events that have, for example, this IP address in it. You can mark events as bad, good, suspicious, or add your own labels to it. And you see it's like a timeline. You can go over, you have a lot of data for each event that's produced by all the parsers that we use. Lots and lots of data for one analyst to tackle, and simply too much data. However, we want to tackle that. So
yes. So this is where threat intelligence comes in. And we split this section into three areas. So binary file classification, where we try to make sense of the files that are on the disks that we're looking at, how we integrate third-party intelligence into Timesketch, and how we are using Sigma in Timesketch. So we see binary file classification, or file classification in general, as a twofold problem. The first one is to cut out the noise of our disk images using known provenance of files. For this, we use a tool called Hasher that was recently released by our coworker Michał, who's on our team. And it basically goes through a bunch of base images of different operating systems, and is going to produce a hash of them and store them in a database. We have a corresponding Timesketch analyzer that just does a massive join of the 4 million events in our timeline, the n million hashes that are in that database, and just tags events accordingly. So if a file is already known or is known to be in the Windows base image, you won't say it's benign, but at least you know where it's coming from, and you know it doesn't require more scrutiny per se. Maybe, you know, lolbins are being used by attackers more and more. Maybe they're using it, but at least you know where it's coming from, and you know it's not extraneous.
And you create your own hash set. So if you have your own custom images, you can ingest them in this database. So it's not something we produce. It's something that you can produce on your own.
Yeah, we don't currently provide base images, even of images that are in GCP. We don't provide hashes for that, but you can use them on your own corp images to provide a baseline of what you know exists. Or at least, you know, if the Windows base image turns out to be compromised, then maybe you have other problems that are not related to your timeline. Yes, we also use APIs, or we can use APIs like VariStotal's known distributors, which works in a very similar way to Hasher. Also hash lookup by Circle, which will tell you if a hash comes from a place that they know of. That's a pretty cool service. And very recently, as recently as yesterday, our coworkers Michał and Janusz published a blog post in OSDFIR blog about exactly how they have used Hasher in an investigation where they really easily narrow down the malware by just pruning out everything that is not interesting. So in a typical timeline, maybe you can have 1.2 million events, but if you then filter out all the things that are known hasher tags, then you'll find that you reduce your data set to 300K events. So that's still a lot. But you know, you can combine this with a bunch of other queries like, okay, if it's not been seen, but it's been seen by VariStotal and the score is 0, then you narrow it down to 2K events. So that's, you know, still pretty interesting, or at least it may provide a good starting point to your investigation. So you go from 1.2 million events to 2K events, which is pretty cool. File classification also goes the other way. We can also use file classification to find bad stuff in our disks. So one thing that I didn't mention before is that this known provenance works on hashes, and Plazo will hash, or you can hash files before shoving them into Timesketch, and Timesketch usually will have the hash of the files that it's looking for. However, it will not have the contents of the files. So if you want to use, like we do, Yara rules on those files, then you will have to send them upstream in the pipeline, because you need access to the file contents in order to look into them. Timesketch has two main ingest options. One is CSV files, and the other is Plazo files.
And JSON.
And JSON.
We can do JSON.
Who here knows about Plazo and log to timeline? Who uses it on a daily basis? One person there, 2 people, yeah, great. Yes, so one little known fact about Plazo is it can also ingest Yara files. So you can tell Plazo to run on a disk image you can give it a set of Yara rules, and it will process your timeline, and it will output events that have this Yara rule, and it will tag events that match the Yara rules. Timesketch can understand those tags, and then you can filter on them. So this is a demo of how to use the log2timeline Docker image. For those of you who don't know, log2timeline in Plazo, I know that it's historically been a little painful to use and install, but with Docker it works really well. So you can see here that the malware, bad malware Yara rule is looking for a string in the badfile.txt file. So we're just going to run the Docker container by providing this Yara rule. Plazo is going to do its Plazo thing. The dark background is probably not best for this presentation. We run the same command with psort, and we say, OK, now we're really interested in the Yara match additional fields of our timeline. So the output that we're expecting now is a CSV that contains, for each file system event, the tags or not that have matched this thing. So if we grep our rule name in the file, then we see that all the 3 events for modification, creation, and access are matching our rule, which is pretty cool.
And you can use that outside of Timesketch. So if you don't like Timesketch but still want to do that and ingest your CSV file into Excel, that's fine. It works.
Yeah, we know that Excel runs the world. But yes, we encourage everyone to use Timesketch for this because you can do cool stuff like this. So you can also use Yara rules not only to highlight maliciousness, but also to classify files. So you can be interested in all files that are PE executables, or ELF files, or Macro, or whatever. As you can see here, if you filter all the files in your timelines by all the ones that are PEs, then you already get a reduced number. And you could also say, like, OK, show me all files that I know are executables, but do not end in exe or DLL. And that maybe will surface extra badness. You can also highlight what is bad. So if you provide Plazo with only a set of Yara rules that are designed to capture malware, then having a query like this, like I want to know if there's a Yara match, and if the Yara match is not empty, then it will only show you the files that are matching your bad Yara rule set. In this example here, we're also using files that are matching everything, rules that are matching everything, so we have a pretty big number of files. But you can also say, OK, I'm looking for this rule. I know that this is what I'm looking for, so I want to see if I have any events that match this. And then you go from a million of events to 4 events, which are the ones that have your file in them. And if you're really lazy or you really don't know which Yara rules you're sending, because you're sending lots of them, you can also see it's auto-populated in the tags section of the quick search menu in Timesketch. It will automatically look that for you, which is pretty handy. Third-party intelligence, that's the second part of what we wanted to show today. So I work on my free time on a platform called Yeti. Yeti is supposed to be a threat intelligence repo that is very, very closely mapped to Stix2 models. I extended it to provide indicator formats that are not the ones that Stix2 uses, because I cannot deal with those. But I came up with one called x-regex. And that's just a regular expression that you can filter on wherever you want. So the idea behind this analyzer, so the analyzer in Timesketch is a task that is going to run in the background on a timeline. The idea is to grab all the regexes from Yeti, run them through the timeline, tag and annotate matches, and be done with that. So in this example, I want to add a regular expression to this intrusion set I've been tracking as true-false gang. They're using a tool called falserat. And I already have one regular expression matching falserat, which is the drop path. And you'll be surprised. If you see this in your systems, it's probably pretty bad. So user bin false, this is the one that we have. But I want to add another one. So I'm just going to add the second version of their RADs, which, as you probably suspect, is user bin true. But this could be any kind of regular expression. In this case, I just wanted to make it simple for the demo. So I just select validation, kill chain stages. This is all very closely mapped to Stix2. Then all I need to do is draw the link between the regular expression and the rat that we're tracking. So I see the relationship exists, and I'm just going to confirm that in this false strat, I can see both regular expressions. So there they are. I switch back to Timesketch. I go to the analyzers. I pick the timeline I want to run this on, pick the analyzer. And this is running on 1.4 million events. It's the same timeline always, as we've seen before. And in a few seconds, it found 2 indicators. Surprise, surprise. This is a native Linux system. And it added them to the intelligence view. So you can see there, OK, this is what we found. User bin false. It was tagged with the entity associated with it. And I can preview the results from there. If I go to the quick search menu, I can see there's like comments and tags and already a saved search that will bring me directly to the results of my regular expressions. So in that way, you can have a team that is just busy extracting indicators from malware or stuff like that. They just add this to Yeti, and then this gets cloned back and immediately reported back to Timesketch. So you could do the same mechanism with MISP, OpenCTI, VirusTotal, any kind of repo that stores threat intelligence that you can think of. And as an alternative way, so in this case, we saw that this is mostly Timesketch querying the system, getting all the indicators, and running them on a timeline. So this is pretty efficient in terms of performance. But if you want your intelligence to stay within your threat intelligence platform, you can also aggregate timelines and aggregate hashes or domain names and so on in your timeline, ship that to your intelligence system, have your intelligence system decide which events are good or bad, and then once you get those results, you can just go back to Timesketch and tag everything. That's another way if you don't want your intelligence to leave your threat intel platform.
Okay, so those were now like very technical things, how you can like decrease the haystack that you're looking at. However, we found that this still doesn't scale. We have a team that has different like strengths and weaknesses. So how do we share what we know amongst the team? And one of the first things that I started to work on like 2 years ago is how can we make use of Sigma in Timesketch? So Sigma, for those who have not heard about it, it's like for log files, what's Nord is for network traffic, and Yara for files. In the past, we used Sigma rules and read them from disk and executed the queries. In the timeline, it was a pain. It was a pain to maintain. So we changed that, and now we have a nice editor in the UI where you can maintain your rules and test them out. At the moment, there is still a warning, like don't try to put all the Sigma rules that are in the GitHub Sigma repository into Timesketch. It will create thousands of queries and will kill your open search instance. B, if there is not the right mapping, you will simply have too many false positives. And C, it doesn't make sense. So think about which rules you want to reuse. However, if you have a good curated list of Sigma rules, you can use the Sigma analyzer to go over your timelines on a regular basis, to highlight stuff in your current investigations, but also in the past investigations, to surface stuff that can be Sigma rules that you created in your investigations, but those could be rules from other teams to help you surface stuff that you might have missed in the past. So here is what it currently looks like. So you have a Sigma rule on the right side, and the Sigma rule itself is a YAML file. It will be translated to an open search query that you can see, and then it's simply executed, and you have an editor. If you try to remove fields like the ID, it will tell you, oh, don't do that. It's not a valid Sigma rule anymore. So it's, I think, nicer to maintain the rules that way instead of on disk. But we have one more thing, and this is something I'm very excited about, and I guess that this will take it to the next level, is like investigative scenarios. I have the problem, let's say, I have a little bit of knowledge about Windows systems, but I'm faced with a Mac system. Like, what do I need to look for on the Mac system? Tom Shop is not around, he's on vacation, so what do? I page him. But that doesn't scale, so how can we share that knowledge? Usually, you start with something like triaging the system, but even such a basic task at that is different from person to person on what they're looking for. So you might ask questions like, what is the operating system? What is the version? What is the local time setting? What users are on the system? All those questions can be answered in a timeline context, but you have to remember the queries. And as I said, I'm bad with remembering stuff. So our idea was to codify what the analyst is looking for, and we call this scenarios. So here's like a mock on how it will look like in the future. So on the right side, you have different scenarios. So let's say we have the scenario of a compromise assessment. You have one system that you want to triage, and then in that playbook, in that scenario, you have steps like, are there signs for lateral movements? Are there signs of persistence? Are there signs for defense evasion, initial access? And then each of those facets will show you several questions that like a human can understand. And then the system will suggest you some queries that are either stored in Timesketch already. It might say, hey, run those Sigma rules. It might say, hey, run this analyzer to connect to VirusTotal to get more information. And then you can, or the analyst can mark, okay, I checked it. There are no signs of lateral movement. Or you can say someone else needs to look at that. But it's a way more guided approach to timeline analysis, versus here's the data, deal with it. So this is our attempt to like spread knowledge across the team. Our idea there is to share also scenarios that we think are critical, like compromise assessment is almost always the same thing. But you might have your own scenarios that you run, or you might just do something extra. You have data sources that we don't have access to. You might have use cases. So you can edit all those scenarios on your own instance, add new scenarios. You can share back scenarios if you want. So that's pretty cool.
All right, cool. So this is time for the outlook and the recap. I thought it would be interesting to talk a little bit about, take a step back and talk a little bit about how we feel about time and timelines. Timelines are a little bit complicated, and they have their limits, right? Because we've been talking so far about timelines that have 4 million events, and they're all ordered by time, sure. But is that the best way to visualize all this data? We all know that investigations are not linear. We start from one point, then we go to another, and then we go back to this thing that we saw because of a hunch. And then we find things, and then we go to this other data source that we need. And not all data sources can be placed in a timeline. How do you place a string that you found in memory on a timeline? How do you place file handles? How do you place a lot of other things that you would like to place, but you cannot place because there's no timestamp? And even if there were, maybe it's a different type of thing. Maybe the timestamp is not really relevant. Maybe it's set to epoch 0, and then it shows up at the end of your timeline, and you'll miss it. So how do you work around this? How do you figure out how to better visualize data other than a huge Excel file with millions of rows?
The next thing I would like to talk about, because there might also be occasions where you have relative time-based events. So let's say you have a sandbox, you execute a sample, and you pull the timeline of that execution. It doesn't matter if it was the 1st of January or the 25th of December. What matters is like 5 minutes after you executed that sample, this and that happened. So how can you overlay the knowledge that you have from your sandbox over your real life case? Like, oh, you saw in the sandbox 5 minutes after there's a DNS query to that domain. Do you see the same thing on the system that you think is affected by the same malware? So how to navigate this problem is something that we hope to tackle in the future. Next up is like timeline anonymization and sharing. That might be in your environment, but also outside. So let's say I'm investigating a case. I'm actually not interested to know that the owner of the system is Tom Chop. So this type of information could be redacted. But maybe there is value once I investigated that MacBook that I share the timeline with the wider community or other teams. But how can I remove the PII from that timeline? Because again, it doesn't matter that it was him who got infected. It's interesting that there is a machine that got infected. So how can we remove Tom Chop from that timeline without tampering the evidence? And last point is yours.
It's mine, yes. We talk about relative time events, things that happen in other places, in sandboxes, and we also want to know how we can include this information in our millions of events. So we have millions of sandbox detonations, we have millions of events per timeline, we have hundreds of timelines, thousands of timelines even. Could we do some kind of statistical analysis on these events to figure out patterns? Did you say machine learning? I didn't know.
No.
It wasn't me. Anyways, these are things, we don't really have the answers to them. We want to experiment more and see where we can reach and what cool stuff we can find in between. But yes, so this is the recap. If you want to take one picture of this presentation, it has to be this one and the next one where we link to all our GitHub repos. But basically, Timesketch has new features. It has a cool new intelligence view. It has 2 new analyzers, one for Hasher and one for Yeti. You can also add your own analyzers for your own internal systems. It's pretty simple to do. There's a new Sigma editor, investigative questions. Little known fact as well, Plazo can work with Yara. This feature exists for a long time, but you might want to take it home. And you can also filter those in Timesketch now. And yes, number 3 is that maybe timeline analysis doesn't show us the whole picture, and it has its limits. So who knows what's next, but we still need to keep researching on this. So we talked about a bunch of tools today. Here's the GitHub repo links. The ones that are in blue, you just add github.com in front of them, and it should take you to the webpage. Alex, do you have any final words?
We have stickers.
Okay. Thanks, everyone, for your attention.